Alright, today the main question that we're going to be considering is this one. When are functions equal to their Taylor series? So far we've looked at examples like e to the x, sine of x, and cosine of x. And we basically said, well, they're always equal to their Taylor series, but we haven't explained why at all. And so that's what we're going to do today, is explain why the function is equal to its Taylor series. Before we can do that, we need a little bit of vocabulary to talk about this problem. We're going to start with this. So if I take a partial sum of a Taylor series, so we add up just like the first n terms, I call it a Taylor polynomial. And the reason for this is going to be pretty clear. So let's take a look at the sum from k equals 0 to n of this power series ck x minus a to the k. Okay, so when we cut off at this finite index n, we are left with just a polynomial. So it looks like c0 plus c1 times x minus a plus c2 times x minus a squared, and so on until we get to cn x minus a to the n. Okay. We call it an nth degree Taylor polynomial. If the polynomial is degree n. So in this example, we have an nth degree Taylor polynomial. Okay, and this is, again, a partial sum for our Taylor series. As an example, let's find the third degree Taylor polynomial for f of x equals sine of x. And the notation we're going to use for this is T3 of x. So the T is for Taylor. The 3 tells us the degree of the Taylor polynomial. Okay, so our first term in the Taylor series for sine of x is x. And then the next term is negative x cubed over 3 factorial. And this is degree 3. So we're all done. Let's define Rn of x, the remainder at x, to be equal to the difference between the value of the function at x and the nth Taylor polynomial at x. So another way of writing this is f of x minus the sum from k equals 0 to n of the kth derivative at a over k factorial times x minus a to the k. So this is the partial sum. If we can show that the limit as n goes to infinity of this remainder function at x is equal to the 0, well, that means that the limit as n goes to infinity of f of x minus the nth partial sum of the Taylor series is equal to 0. So f of x then is equal to the limit as n goes to infinity of Tn of x, the nth Taylor polynomial. And so our function at x is equal to its Taylor series at x. At x. Okay, so our goal is going to be to come up with a way to show that the remainder term of functions is to bound when what's happening to the remainder terms of functions, to show that their limit is equal to 0 for cases like e to the x, sine x, and cosine x.